Hello my friends, and welcome again to my video channel. Today we continue our work on this small function generator PM5127. We will start with the alignment, but before we do the alignment I've decided to swap the electrolytic caps inside. They are not so much, and these are the old blue types. I don't like them very much. I think these are not the best ones. On the other hand, I really have never seen a faulty one of this type. But I will swap the caps. It's not a big job, only some caps. So let's start. Nearly all capacitors are accessible from the bottom side of the board, except the electrolytics on the power supply. Here we have the big ones, the two big ones, and for smaller ones it's necessary to remove the backplane with a transformer. The power transformer here cannot be removed so easily, so it's necessary to remove the whole backplane. There's another screw inside. You can see it here on the power transformer. The hole is there for it. This screw also has to be removed. To get access to the screws of the backplane, it's necessary to remove the side shields. And to remove side shields, it's necessary to remove the handle and the front to get better access. Well, that's it. Now we can replace the electrolytic caps, the two big ones and the four smaller ones. All capacitors are swapped now, and I want to show you one thing. Between this power transistor and this power resistor, and both get hot during operation, I checked it, there was an electrolytic cap installed. This design is a designed obsolescence. It's not a good idea to have an electrolytic cap between these two heat sources. So I swapped this capacitor to the rear side or bottom side, and we can see it here. This is its cap, and there it will not be roasted. It can survive for a long time. It's a better place for such a component. These are the old electrolytic caps. They are all okay. I measured them regarding capacity, regarding losses, tangents delta or quality factor, and isolation. Some have a little bit more capacity, 10 or 20% more than specified, but they have no leakage. The internal leakage resistance is well above 50 megohm, partially 100 megohms. So it's a very, very good bunch of capacitors, but I'm not sure how long they will work, because this generator was obviously not used for many years, and when we have electrical components, especially capacitors, and they have to operate after such a long time, maybe they will fail within hours. That's my experience. So the caps should be swapped. That was my decision. Maybe it was not necessary, but on the other hand, it's not a question of money, only some euros, so I think it's okay to swap them and replace them by new ones. Now we can start with the alignment. There is a small problem. I have the newer version 5127/03. The manual I found on the net is a /01 version. There's obviously one decisive difference. The version here, 03, has a different sign shaper. And the sign shaper is not described in the manual what I have. It is a different circuit. I think a different method. It cannot be compared to the rest. Seems to be identical and original. The alignment points are the same. The trim pots and trim capacitors are in the same place. Only the so-called sign shaper, I will show it. It is this section here. This looks different. Here's an integrated circuit in it. I couldn't find in the net how it works. It's a very mystery circuit, and there are only some components around. 1 transistor, 4 trimmers. I don't know how to set them, but I have an idea how to check it with the best method. This integrated circuit has a designation H7505. H7505. Couldn't find any information about it in the net. No chance. Anyhow, I have an idea how to do it, but first I will start with the rest of the function generator, the oscillator part, the oscillator section, frequency setting of the pot in the front, and so on. The alignment starts with a check of the power supply. One step which is not stated in the manual I do always is to check the ripple on the filter caps behind the bridge rectifiers. That's a negative voltage. We have here 10 volt per division, so we have a minus 35 volt, and important to see that the ripple is 100 Hertz. We have here 10 milliseconds per division. This indicates clearly that the bridge rectifier is okay. If you would have a faulty diode in the bridge rectifier, one of the peaks would be missing, and we would have not a full bridge rectifier. It only would be a half wave rectifier, but here we have indeed a full wave rectifier. It's a minus volt, and the positive volt is also okay. Same here, so we can say the bridge rectifier and filter caps are okay. The next check is the supply voltages plus minus 15 volt, which can be adjusted, but it is okay. Should be plus minus 5 millivolt, and the negative one is also okay. No need for any further action. Next step is to measure the symmetry of the output of the triangle of the generator itself. The generator here works with a triangle generator, charging upper capacitor and discharging it. This makes a triangle, and the other two waveforms, square wave and sine wave, are derived from it. And the output has to be absolute symmetrical. And this pot here is used to set it, and you see when I vary this pot, the lower amplitude goes up and down. The upper is more or less constant, but this is not constant, and it has to be set that this amplitude and this amplitude is identical, or the resulting voltage level, DC voltage level, is 0. So we can measure it with a multimeter and align it to the absolute 0 point. It is stated with, I think, 5 millivolt, but it is not possible to have constant 5 millivolt. It's always jumping around. It's not important. Yes, now it's okay. This is the absolute 0 point. And so this voltage is symmetrical. Now we have here the symmetry of the square wave generator connected to a test point. Frequency is 0.1 Hertz. So we see the jumping between minus and plus voltage, and this should be the same voltage, minus 2.3 and plus 2.3. It has to be symmetrical. I managed to adjust it here with this pot so that these two voltages are symmetrical, and the square wave generator, the trigger, is symmetric according to the manual. The millivolt meter is connected to the wiper and to one end of this pot, and it should be set to approximately 3 millivolt or less, and this should be beyond the last tick, but we see it is not correct. Okay, I had removed it and brought it back with the feeling of my thumb, And when we see we have no voltage variation, and suddenly we have 300 millivolt, but it is too far from the 0 point, so this should be, this indicator, this pointer should be there, so I have to move the whole scale into this direction. This is too close. Okay. Looks better. I will fix it in this position and then we can continue. Now the alignment of the frequency scale of the DC levels. The duty cycle has to be unsoldered on the board as described in the manual. The digital multimeter is connected to the three checkpoints here, the 3 and 5, and the output, which is channel 2. It is set to square wave and we measure the time, the positive time and the negative time. The duty cycle is nearly 49 something percent and the width is 370 microsecond and the other is 372 or so microsecond, the measure time, and this is in the setting of 10 of the scale. And when I reduce it down to the lowest level, this voltage should be, instead of 6.9, 100 of it, which is 0.69 is alignment with the pot, and the T10 plus and minus should be 100 times. I need to bring the scope on the right measurement, so we have 100 times, that is 37 and 37 milliseconds. So the duty cycle is again 50% as it was before. This can be set with the other trimmers. I've done it with these trimmers. For this job is done, and now I have to resolder the duty cycle of the pot again. And this job is also done. It was a little bit difficult for me to understand because the manual here is very cryptic and there are some typing errors in it. I always thought what it is. Then there was some calculation signs missing, but now I understood it. That the scale, the mechanical scale, has the full voltage range, and then we can align the frequencies in detail. Now we can align the various different frequency ranges. There are some pots in it to check the frequency. The start at 10. The lower frequency at 1 has been set with the previous method. By the way, I had a little bit to readjust this scale here, the knob, to get a better setting range of the pots. Otherwise, one of the pots was at its end. Well, for example, at setting 1K and frequency setting 10, we should have 10 kilohertz. With the pot 613, we can align it a little bit better for exactly 10 kilohertz. 997, okay. Let's check at 1 kilohertz, that's okay. We're a little bit high, but it's difficult to adjust these pots. They are very touchy. 999, okay. And here we have 1. Okay, that's within the range. Check linearity at 5. Okay, 5 kilohertz, 5.0. That's okay. The linearity of the scale is rather good because it's a wire wound pot, not a film, metal or carbon film pot. It's a wire round which is very linear of the whole range. Next one is times 10. Frequency should be at setting 10, should be 100 Hertz. We have 100 Hertz, 100.3, and at 1 we should have 10 Hertz. Yes, that's okay. I don't show all the steps. It's boring, I think. So the frequency scale will be adjusted as it is specified here. And I think it can be done rather easily. There was one speciality in the highest range, times 100 kilo ohm, which goes from 100 kilo ohm to 1 megahertz. It has to be adjusted in the frequency 3.5, that means 350 kilohertz. And there is a trim pot, a trim capacitor, sorry, not a pot, a capacitor, where we should set the frequency to exactly 350. Also very touchy. And then we check at 100 kilohertz. It is 100 kilohertz, and at 1 megahertz. .04, and it is specified with 1.04, 1000 plus minus 40. It is 40. Frequency is a little bit too high. Here it is okay. We could go down a little bit at 3.5, okay, 350 and something, to reduce it here a little bit. And let's go to 1 megahertz again. Okay, 3.6, 36 kilohertz above, and 40 is permitted. Let's check a linearity at, for example, 750, 762, 800, 820, 600, 606. 500, okay. So it's not a high frequency generator. 2.5, 2.46, and at 100, 99.9. Well, the frequency ranges are all set and they're okay. Now we can go to the next step. Now we have to check the duty cycle setting, whether it's okay or not, done in the range times 1K, 10 kilohertz setting, as it is stated. And then we should measure the duty cycle. I do it with the scope, it's easier. Measure, come on. Yes, I could use my mouse, but I'm too lazy. Positive duty. We need a complete wave here, 49.9%. When we go down to 10%, we switch duty cycle on. This is 8.3. What do they say? Times, it is 10 plus minus 1. Okay, it's a little bit less than 10. Not a big problem. And then we set it to 90%. We measure 90, duty cycle 90 something. They measured T positive by T negative, the inverse one. It's also plus minus 2. We have 91. Okay, it is within the limit. No big deal. So we can go to the next step. Now we check the duty cycle, that the setting of the duty cycle does not have a big influence on the frequency. It is set to 10 kilohertz, 1 kilohertz times 10. We have 10 kilohertz. And when we switch on the duty cycle and vary it from 10 to 90%, the frequency should not change more than plus minus 1 kilohertz. Okay, it's 9.1. It's the lowest end. We come to 10. And then it shouldn't not be more than this 10.1. Okay. Let's set it to 10 kilohertz. Sorry, duty cycle is off. 10 kilohertz with duty cycle on. We vary between 10.18, 10.2 down to 9.1. So we are within the range of plus minus 1 kilohertz. Yes, it is stated 10 plus minus 1 kilohertz. It's a rather big variation of the frequency. 10 kilohertz, it's plus minus 10% in the frequency. It is not so good when we change a duty cycle, but such simple generators are no precision instruments. They are rather cheap, and that's one of the disadvantages. So we would need an external frequency counter on the output here, for example, on the TTL output. Next step is to check the frequency offset plus minus 5%. By the way, I've changed the knob. When I took the old knob out and I removed this cap, the cap was damaged. This old plastic broke. So I bought a new knob and a new cap for it. This new knob is a little bit thicker, bigger, has a little bit more diameter and therefore more grip. It's good. Set to 10 kilohertz. I go down to minus 5%. It's 9.56. Okay, not exactly 5%, and plus 5% is 10.569. I could readjust this knob a little bit, but I don't do it. It's not necessary. We can live with it. So we could mechanically adjust it a little bit better, but what for? Makes no sense. Now we check the sweep input connector. Frequency is set to 5.5 kilohertz according to the manual. When we apply plus 2.25 volt. This is minus, this is plus. Of course we have to go to DC. 2.25. We should measure 10 kilohertz. Plus minus, what is this? Plus minus 0.3, 993, that's okay. And when we swap the direction, when we go minus and plus, with inverse polarity, frequency should be 1 kilohertz plus minus 0.3. We have 1 plus 1, could be 1 plus 3 kilohertz, so it's also okay. The sweep input also works as it should. These are the last test, and now we have to set the distortion of the sine shaper with a distortion measuring bridge. Yes, as it is stated. This is a setup for the measurement of the distortion. Distortion Analyzer Hewlett-Packard 334A. It's a distortion analyzer who runs up to 600 kHz fundamental frequency. The output of the sine shaper here is connected via this probe to the input of the analyzer in parallel via this cable. The scope is connected and shows the yellow curve. The yellow curve is the input of the analyzer. That means the output of the sine shaper. We do not use in the first step this output from the generator. We use the internal connection to the sine shaper. Here we have a second connection. This is the output of the analyzer. This is a bridge output. It is connected to the blue line, to the blue scale. In the moment we have function set level. That means the pot is set to maximum. We see here when I go to 100%. This is 1. Frequency set times 1K, and 10 is 10K, approximately 10 kHz, which is same here, times 1K and 10. 10 kHz is the frequency where the manual states that the alignment of the distortion or best linearity has to be done. Well, in the moment we have set to 100%, and then we go to the measurement of the distortion from level to distortion. And this means the bridge is switched on, and now we have to adjust the frequency for null operation. And here is a balance. This is a compensation of the resistive component. And when we have nearly 0, then we go down from level is set 0 or 100%, 0 dB. This is 10%. We still can adjust it with fine tune and go down. It's a little bit touchy for very high attenuations. Can go one step further. Now we have here the mode manual automatic. When the alignment is done, then we can do following. We switch to automatic. Automatic means that the bridge internal, which is made by resistors, by resistors and a capacitor, this bridge is automatically aligned or nulled with a photoelectric circuit. There are 2 incandescent bulbs in it which control 2 optical resistors, and these resistors are controlled in such a way by amplitude and phase that the alignment is optimum. And you see it goes down to 0, and then I can increase the sensitivity much more. Then I have full scale 0.3. This 100, it's 0.3%. Full sensitivity, we have now a distortion level of 0.1%. This is 0.3 and this is 0.1. And then we can align the pots, and there are several pots on it. And here we see the sine wave, the output of the sine shaper, and this is a distortion. It is of course magnified, and the trigger is set to the channel 1, to the yellow channel. And when I align the pots we have here for the best linearity, we see there are coming the peaks up, and these peaks cause the distortion to increase. And what are these peaks? They're exactly here and here. And this is a point where the triangle is switched from charging, discharging, charging, discharging. Charging, discharging, and there are the switching peaks. And with these pots, these switching peaks can be optimized. And the other 2 pots have a little bit of influence, but not very much. And it's a play where we can adjust it for hours, but we have here the best result, which is less than 0.1%. We are below 0.1% distortion, total harmonic distortion. and we see here there is a little bit of ripple. We can adjust it down to 0. Can I align it with this one? No. And so we can play with it for hours. For hours and hours, but again we are below 0.1%. Specified in the sheet here is in the alignment sheet to be better than 2.5%. 2.5% better. We'll go up in the range to 3% full scale. This is 3% full scale. 2.5 would be here, and we are here. So we are ways better than the requirement of the manual. When I go to 0.1% full scale, okay, a little bit noisy, but it is again less than 0.1%. We can try to improve it, but again it is not necessary. I prefer this range, it is better. Not to be such sensitive. Doesn't help. Okay, I think this is the best solution. Now this monitor output is very useful. You see the distortion related to the original sine wave, and we can optimize it. Well, I leave it as it is, 0.1%. At the distortion, at the output of the sine shaper is much better than required. And now the manual states a check of the output. We are again on sine wave, amplitude is maximum, 0 dB attenuation. I've set the level to 100%, and we can expect a little bit worse THD, total harmonic distortion, due to the amplifier which is now used. The output amplifier is in series with the sine shaper. So let's go to the distortion measurement and do it manually. Okay, it is still okay. %. It is 0.3%. Oh, okay, it's nearly the same. And 0.1%. Oops, didn't synchronize. Maybe the manual alignment is not perfect, or the frequency drifted a little bit. Ah, yes, the frequency has drifted a little bit. The presetting has to be okay for the analyzer, otherwise the automatic function doesn't work. 1%, 0.3%, yes, it's the same as before. We have the same picture, 0.1%, yes, exactly the same value. It is stated should be better than 34 dB. We can also measure it in decibels. When I do the set level to the 0 dB position, I use 0 dB. And then I go to the distortion, go down 10 dB, from 0 dB, minus 10, minus 20, minus 30, minus 40, minus 40 dB, and additional minus 6, minus 46 dB. Sorry, I made a mistake. I have forgotten to switch onto the automatic mode. The the picture was not so good. In automatic mode we get minus 60 dB, nearly minus 60 dB. When I go to 0 and set level, we have 0 dB again. Distortion meter, minus 10, 20, 30, 40. Automatic, minus 50, minus 60. Okay. Minus 50 and minus 60. Sometimes it doesn't lock correctly. Minus 60 dBm and 1 dB more. So we have minus 60 dB instead of minus 34 dB. That was the same result as we had before. Okay, I think it's a very good result, and we can live with it. Always the operation of the instrument. Read the manual and understand it. A short theory. The specification says 2.5% THD. This equals 34 dB, minus 34 dB. We can calculate it. It is nearly 34, it is 32, but doesn't matter. I measured better than 0.1, let's say 0.09%, minus 61 dB. Is this true, this relation? Let's calculate it. The relation between 2.5% and 0.09% is 27.8. Let's calculate the decibels. 20 times logarithm from 27.8. 20 times 0.144 is 28.9 dB. When we have 34 dB and we are better, then we can add this 28 and we come to 62.9 decibels. That's what we have measured nearly. We have measured 61 dB difference. That's okay. We have tolerances, measurement tolerances, and this spec is also not 100% okay. So it is good. The measurement and the theory is okay. We can live with it. The last check is the square wave. Regarding ringing, overshoot, it is measured at 10K times 10, it's 100 kilohertz. The square wave is perfect. There was a trimmer in it, but the trimmer is okay in the amplifier stage, so it was not necessary to readjust it. As you can see, we have a perfect square wave. No overshoot, no undershoot, nothing. It's okay. The DC offset levels are also checked and okay. That with low output voltage, or for example when we have no signal connected, no signal chosen, then the level is 0 in the range of some millivolt. I think it's 20 or 30 millivolt according to the spec. That's okay. Now we are at the end of this little project with this small function generator. The only problems this generator really had were the switches, bad contacts in the switches. Cleaning was sufficient. Thorough cleaning, a realignment is advisable with such an old equipment. It is from the late 70s or early 80s, so it is roughly more than 40 years old. But it's in very good optical shape. I assume it was not very often used, and it was stored in a cubicle or anywhere else. It was warm and dry, especially dry stored. No dust. The housing was rather clean, also inside. This generator is a universal generator for many applications. Amplifier measurement, sine wave, frequency response. The sine wave is very clean, THD less than 0.1%. It's the data of a good RC oscillator. Only very good RC oscillators are better. Square wave is okay for square wave response of an amplifier and other applications in the lab. Stay healthy, stay tuned. See you on this channel.